Hey everyone, and welcome back. Today we are taking a really fascinating look at the absolute foundation of everyday math. We're launching into a masterclass explainer covering 6th grade decimal operations. But listen, we aren't just going to sit here and memorize dry rules. We're actually going to uncover the secret behind-the-scenes life of the decimal point, and we're keeping it completely grounded in the practical math you use every single day.
To show you why this actually matters, just picture this for a second. You're grabbing breakfast at the Sunrise Cafe. The barista hands you your receipt. Your subtotal is $44.20, and the tax is $3.54. So how much do you owe? Well, if you misplace the decimal point while calculating this, you could literally end up paying over $400 for coffee and some toast. So instantly, we can see that understanding exactly where this little dot goes isn't just a textbook exercise, right? It's a pretty vital life skill.
Okay, let's dive right into our roadmap for this explainer. We'll start with adding and subtracting, tackle multiplying, then dividing by whole numbers, conquer dividing by decimals, and then wrap the whole shebang up with a quick review.
All right, section 1, adding and subtracting decimals, or as I like to call it, holding the line.
I call it holding the line because when we add or subtract, the decimal point's secret life is that it wants to stand completely, absolutely still. Here's the standard algorithm. Step 1, line up the numbers based on their place value. Step 2, include any place values. Those are those vital little zeros that keep our columns super neat. And step 3, just add or subtract like place values straight down. Emphasizing that alignment and dropping in those placeholder zeros, that is absolutely your golden rule right here.
Let's actually bring back that Sunrise Cafe receipt to see this in action. We're setting up $44.20 plus $3.54. Check out how perfectly vertical this setup is. The ones place is right over the ones place, the tenths over the tenths. The decimal points are stacked directly on top of each other, forming this perfect anchor line. You add straight down, and boom, there it is, $47.74. Notice how the decimal point simply dropped straight down into the exact same spot in the sum? Keeping it anchored meant our math stayed organized and perfectly accurate. So yeah, no $400 coffee today.
Moving right along to section 2, multiplying decimals, which is all about the jumping point.
Now, in multiplication, the decimal point suddenly wakes up. It gets active. It stops standing still and literally starts jumping. The standard algorithm here actually flips the script on what we just learned. First, you set up the problem and multiply the digits as usual, completely ignoring the decimal. Seriously, there is no need to line up the decimals vertically for this one. Then, the magic happens. You count up the total number of digits to the right of the decimal in both of your original factors combined. Finally, you just put that exact same number of digits behind the decimal in your final product.
And this brilliantly illustrates why that jumping rule works. You know, before we even touch the standard algorithm, we can use visual area models like these to estimate solutions and kind of wrap our heads around the patterns. Looking at 2.7 times 1.4 or 0.5 times 2.5 on a grid, you can physically see the size of the partial products. It grounds the math in reality. It proves that our answer has to make logical sense based on the actual size of the numbers we're multiplying.
But you know, what's really interesting is how fast things go wrong if we forget the jumping rule. We have two students here, Sydney and Jorge. Sydney multiplied 62.8 by 3.7 and got 2,323.60. Jorge multiplied 50.9 by 4.8 and got 244.32. Take a look. Can you spot who made the mistake? Well, look at Sydney's work. The number 62.8 has one digit behind the decimal. 3.7 has one digit behind the decimal. That's a total of 2 digits. Sydney's actual math digits are totally correct, but our decimal point jumped to the wrong spot. It should really be 232.36. Jorge nailed it.
Let's test this jumping rule with a real-world scenario from our source text. Amber walks her golden retriever 1.87 miles each day after work. If she walks him 5 days a week, how many miles does she walk in total?
Okay, so we multiply the whole numbers, 187 times 5, to get 935. Then we look back at our original factors. The number 1.87 has 2 digits behind the decimal. The number 5 has 0, so our final answer absolutely must have 2 digits behind the decimal. The decimal jumps in 2 spots from the right, giving us a perfect 9.35 miles.
Section 3 already, dividing by whole numbers. Get ready for the upward slide.
So here, the decimal point takes on a brand new vibe. When dividing a decimal by a whole number, it has a very specific upward trajectory. The algorithm is wonderfully simple. Set up your standard long division. You really must keep your place values highly organized here. Then, before you even start doing the actual math, take that decimal point in the dividend and shoot it straight up into the roof of the division house, directly into your quotient. Once it's chilling up there, you literally just divide as usual.
Let's look at another error analysis from our masterclass source. We're dividing 18.66 by 3. Both students shot the decimal straight up correctly, but their answers are different. Marielby says 6.33, Nico says 6.22. If we trace the math, Marielby actually just made a simple division error. When dividing the 6/10 by 3, she wrote a 3 instead of a 2. So the decimal placement was flawless, but it's a great reminder that we still have to do the standard long division accurately. Nico correctly calculated 6.22.
Now, this upward slide, you use it all the time when you're shopping. Think about trying to find the unit rate at the grocery store. You have a bag of goodies, and the product is priced at $12.84 for a total of 6 ounces. To find the cost per single ounce, we have to divide that decimal, $12.84, by the whole number 6.
We set up the long division, shoot the decimal straight up into the quotient, and just divide. 12 divided by 6 is 2. 8 divided by 6 is 1, with 2 left over. 24 divided by 6 is 4. Bringing the decimal straight up gives us the exact change required, $2.14 per ounce. Easy, right?
And finally, section 4, dividing by a decimal. This is what we call the power slide.
For our final operation, the decimal point actually has to make a lateral shift of power before it can make its upward slide. See, when your divisor, the number outside the house, is a decimal, we have a problem. The standard algorithm demands that we make it a whole number first. To do this, we multiply the divisor by a power of 10, which is really just sliding the decimal point to the right until it's a whole number. But here is the unbreakable golden rule. Whatever you do to the divisor on the outside to make it whole, you absolutely must do the exact same thing to the dividend inside the house. You slide both decimals the exact same number of spaces to the right. Then, bring the decimal straight up and divide.
Let's walk through this specific example from our text together. 210 divided by 3.5. We can't easily divide by 3.5, it's messy. So we multiply 3.5 by 10, basically sliding the decimal one place to the right to make it a clean 35. But because we did that outside, we have to do it inside. Now, 210 has an invisible decimal at the end. We slide it one place to the right, which forces us to add a 0 placeholder, making it 2,100. So our brand new, totally equivalent problem is 2,100 divided by 35. And when we divide 2,100 by 35, we get a clean, beautiful whole number, 60. By shifting the decimal points equally in both numbers, we preserve the true mathematical relationship. We basically changed how the problem looks without changing its actual value at all.
Okay, so the absolute crucial takeaway here is this. The decimal point isn't just a static dot. It behaves totally differently depending on what you're asking it to do. Let's do a quick review of the rule of the point from our masterclass. In addition and subtraction, it stands totally still, so line those place values up. In multiplication, it ignores the initial setup, then counts the digits and jumps at the very end. In division by a whole number, it shoots straight up into the quotient. And in division by a decimal, it slides to the right to make a whole number and then shoots straight up.
We've thoroughly deconstructed the algorithms today, and we've tracked the secret life of the decimal point across every single operation. But remember, this isn't just math on a textbook page. The next time you're comparing the price of apples, calculating yards of fabric, or checking your receipt for that coffee and toast, I really want you to visualize this masterclass. Can you track exactly where that decimal point is moving behind the scenes? Thanks for learning with me today, everyone, and I'll catch you in the next explainer.